Good afternoon. This is Andy Schweitzer, and here is a little informational calculation worksheet on proportional dilutions, molarity calculations of ionic compounds. Pretty important concept to really have mastered as we exit the states of matter chapter, going into things like stoichiometry and being able to do proportional math. But a lot of stuff here. So we will go quickly through this and draw a relative proportions. And this is asking me about one button or two buttons. I have one button. Okay, got it. Okay, thank you very much. Anyway, so we have the equation here. Route the equation for the salt to be Na3P goes to Na plus 1, and there's 3 of them. So weird 3. And then we have our phosphide ion. It says, okay, so now it's saying draw these things, draw relative proportions of quantities of ions in sample A and include 2 water molecules. So first of all, I have an Na plus ion that I'm going to be writing this thing, Na plus ion. And I have a phosphide ion. They come in ratios of 3 to 1. The sodium ion has a full second energy level, and the phosphide ion has a full third energy level. So the phosphide ion, even though there's only one of them, will be bigger than the sodium ion. That is pretty important. Na plus, Na plus, and Na plus. Make sure you show that they are dissociated and separate and considerably smaller than that one. Two water molecules, okay. So this is a positive, so I have my water would be orientated in this direction. Do not put a positive or negative on the water. If you do, you have to put a partial positive and a partial negative. That's a partial positive and a partial negative. Not required, but definitely water does not have a full positive or negative charge. Notice I have the negative of the oxygen going towards the positive cation, and if I were to do it this other way, I would want to make sure I stay away from the other guys. The hydrogen, oxygen, hydrogen, and like that. All right. Determine the dissolving equation. I'll get that already. It's right here. Determine the concentration of Na plus and the other in this solution. So in this case, this Na3PO, just P3P. Notice they come in 3 to 1 ratios. So there's 3 sodiums for every 1 sodium phosphide. So if the solution is 0.2, and I want to show my work for it be Na3P, would be a 1 to 3 ratio, which is 0.6 molarity for the Na plus ions. It's a linear proportion. The phosphide ion, there's one phosphide for every sodium phosphide. So it's going to be 0.2 at a 1 to 1 ratio of Na3P, 2 P's, and therefore it's 0.2. Molarity is the answer for that guy. All right, and then next one says we take this stuff, 50 milliliters of that 100 milliliter sample, so it's just 50 milliliters of the concentration of which is 0.2 molar, and I'm diluting it down to 200 milliliters. So there's a couple ways you can solve this. I'll do it one for each one. I'm just going to do the easier way. I'm going to start with the 0.2 molar of 50 milliliters of volume. And I'm going to use the M1V1 equals M2V2. So that's my concentration of my volume. My ending concentration is what I would like. And my ending volume, V2, very carefully, is V1 plus what you add. That's very important. So this guy is going to be 250 milliliters. Solving for this case. Now I'm using the concentration of the entire solution. So in this case, M2 would be the concentration of the entire solution after I add 50 milliliters of water to it. 200 milliliters of water to it for 250 total. So let's do this. I got 0.2 times 50 divided by 250, and I have 0.04. All right, so my molarity is 0.04. Now that's the molarity of the entire solution, and of course we know that it's a 1 to 3 ratio to the sodium ion, and therefore is now going to be a 0.12 molarity of the Na plus ion, because that is what they want. All right, and the phosphide ion I'll show over here. Now I'm going to use the molarity formula. Molarity equals moles per liter. I want to figure out how many moles are present in my solution, and then just run it again. Once I have my moles, divide by my new volume, and get my new molarity. So I'm going to use this thing twice. First, I'm going to figure out how many moles I have of my original solution. So original solution is 0.2 molar, and it is in a volume of 50 milliliters, 0.05 liters. And then my moles, X, all right, so X moles is, and I'll calculate that, 0.2 times the 0.05 is 0.01. So I have 0.01 moles, now in a larger volume, so less concentrated, of 0.250 liters is 0.04. 0.04, and that's the molarity of the sodium phosphide solution. But since there's one phosphorus for every solution, it is also the phosphide concentration. It's linearly proportional to 1. 1-to-1 ratio. All right, now this one we're asking for a concentration of some ions. All right, determine the concentration of each ion in a sample B. No calculator. So each ion in B. So in B we have Ag and NO3. They're a 1-to-1 ratio. So Ag plus ion is concentration. The brackets mean concentration equals 0.5 molar. All right. And the nitrate ion, NO3 minus 1, concentration will equal also 0.5 molar. That's important. All right. For the next one, sample C, it's a 1-to-1 ratio for the magnesium. So the magnesium 2 plus will equal 0.5 molarity. I'm sorry, it's that particular item is 0.2 molar, so 0.2 molar for the magnesium. And the chloride ion concentration will equal it's 1-to-2 ratio, so I get 2 chlorines every time it breaks apart. So it will double to 0.4 molar. All right, again, some work is skipped there, but it's a 1-to-2 ratio of chloride ions to magnesium chloride. All right, number 5, mix the samples together and B and C together. What are the concentrations for each ion? Again, no calculator. So in this case, I have a beaker, a smaller beaker with 100 milliliters in it, and it's got some ions present in it. And I have another beaker with another 100 milliliters. And again, the fact that there's more ions there doesn't really matter, okay? I'm doubling my volume. By doubling my volume, I will be cutting my concentrations in half, as long as there is not some of X in both sides. So if you look at this, molarity equals moles per liter for the silver of the silver nitrate would be 0.5 molarity equals X over 0.1 liters. So I have 0.0, yep, I have, half of this would be 0.05, okay, moles. Now, I have that number of moles. If I double my volume, I'm just going to divide it by 0.2 liters, or 200 milliliters. I'm dump both these guys together. I have the same number of moles, just in a larger volume. So now imagine a beaker here where I have more volume, but the same stuff in a lesser concentration. So this is going to be 0.5 divided by 2, or 0.05 divided by 2 divided by 0.2 is 0.25. And of course it goes from 0.5 down to 0.25 because I doubled my volume. Again, did I double the moles? No. If there are moles present of this Ag plus ion in both of these, then I have to count for the moles present in the first solution and the moles present in the second solution, add those together so that I would add up my moles and add up my volume. But in this case, the moles are the same, I'll just double my volume. So that's why they're saying no calculator, because I'm doubling, nice and easy number, doubling. So the Ag plus is done. The nitrate would also be the same. NO3, I'm going to put it on the side here. NO3 minus would then just drop in half to 0.25, the same as the silver. The magnesium is normally 0.2, but it gets cut in half to 0.1 molarity. Now the chloride ion, the chloride is a little bit trickier. Because it breaks apart into two pieces, the 0.2 molarity doubles to times 2 to 0.4. But then, of course, we're doubling our volume, which cuts it in half again, back to 0.2, and that is my concentration for the chloride ion. Chloride ion concentration, 0.2. All right. Next, we have a little different sheet here. I'm going to pull this up a little bit bigger here. The back side. All right. Now, in this case, they're plenty big now. I have 100 milliliters of 0.1 molar barium chloride and 100 milliliters of 0.2 molar sodium chloride. All right, so the concentration of each ion in the sample, in sample D, all right, well, this is pretty simple. I just got it 1 to 2, so it's 0.1 molar for the barium 2 plus, and it's 0.2 molar for the chloride ion. I doubled it because it breaks apart into two pieces. And then this guy here, the sodium ion, is 0.2 molar. All right, at a 1-to-1 ratio, 0.2 to 1. And the chloride ion here also is 0.2 molar. Now I notice that the barium and the sodium are present only in individual beakers, but the chlorine is present in both of them. And also notice they have the same concentration. Okay, so mix D and E together, D and E. And what are the concentrations? Well, I'm doubling my volume, so barium's not present in both, either just one, and the volume doubles. So barium ion concentration is going to go from 0.1 down to 0.05 moles per liter. That's going to get cut in half. The sodium ion concentration is going to go from 0.2 down to 0.1 concentration. All right. And the chloride ion concentration. Now this one you can actually calculate if you'd like, but you have 0.2 molar plus 0.2 molar. So we did the molarity equals moles per liter. You'd find that you get a certain number of moles for the sample 1, sample D, and a certain number of moles from sample E, and they are equal. So we'll double our moles. But then the volumes, they're equal too. So they also will be times the liter times 2, 2 times, 2 times. So I end up with the same 0.2 molar, which might make sense. If I'm dumping 0.2 molar into 0.2 molar, I should stay with 0.2 molar. Right. Next up here, I have sample F. Okay, so now the only difference between 8 and 9 is 8 has these nice volumes. Okay, 9 is one where, okay, we're going to have to change it up a little bit and do some little bit more math because the numbers aren't proportional. All right, so determine the concentration of each ion when mixed when we mix sample F and G. Okay, so aluminum starts out at 0.3, all right, and this guy starts out at 0.9. This guy starts out at 0.2. This guy starts out at 0.246, 0.6. So those are the concentrations of the guys that they're starting with, and then we are going to be diluting it. Now this guy, the aluminum is present in both, so I'll wait for that one for last. The nitrate though is 0.9, and it increases from 100 milliliters to 600 milliliters. So it increases 6 times. So the concentration will drop by 6. So let's do the nitrate. The way I would solve this problem is maybe the easiest way is M1V1 equals M2V2. Mimicking this equation, I have 0.9 molar times 100 milliliters. Remember, I can use milliliters in this equation as long as I'm consistent. X concentration times 600 milliliters. And just simply solve for X. 0.9 times 100 divided by 600, and I get 0.15. And this would give me the concentration, just the nitrate ions in this solution. Okay, now the acetate ion, same thing. In this case, I have 500 milliliters of it, so I would expect my answer to be, in this case, quite a bit closer to 0.2. All right. Let's do the math. I have M1 V1 equals M V2 V2, so it goes from 0.2, and then the V1 is 500 milliliters, and then I have, in this case, M2, which is what I'm looking for, and V2, which is going to be my ending volume of 600 milliliters. Again, I'm using the concentration of the actual, the acetate ion was actually 0.6. So I'm going to make this a 0.6 so that I don't have to multiply by a 1 to 3 ratio when I'm done. If I did that, the whole thing, I have to do a 1 to 3 ratio to get the actual acetate ion. So 0.6 is the actual ion concentration. So 0.6 times 500 divided by 600 is point. So that doesn't seem too right. I got 0.6. Oh yes, okay. So that's 0.5. Okay, my X equals 0.5 moles per liter, which it starts at 0.6, ends at 0.5, so it goes down slightly. Okay. In this case, let's make sure here the nitrate ion started at 0.9 and went to 0.15. So that's quite a bit drop, but I went from 1 to 6, so I increased the volume 6 times. So the concentration should have dropped by 6. This should be 1/6 of the original concentration of 0.9. If you take 0.15 times by 6, you should get 0.9. All right, so let's do this aluminum. The aluminum is present in both solutions, so the dilution formula may not be as useful at this point. I'm just going to use the molarity formula, which is what the actual dilution formula really is. Molarity equals moles per liter, 1 for each of these guys. I have a molarity is 0.3 equals X moles over 0.1 liters. I'm just using the standard concentration. It's a 1-to-1 ratio, 1-to-1 ratio, so there's one aluminum in every one. So 0.3 times 0.1 should be 0.03 moles. And then this guy is going to be 0.2 equals X moles over 0.5 liters. So half of that is X equals 0.1 moles per liter, half of that. Actually moles, not moles per liter. So now, in my new solution, when I mix them together, molarity equals moles per liter. I have this molarity, moles, this moles, for a total of 0.0, be 0.1, this is 0.1, 0.13 moles in total volume of 0.6 liters. This is my new concentration. 0.13 divided by 0.6 equals, calculator gave me an error, 0.13 divided by 0.6 equals 0.21 is what they're giving me, equals 0.21 moles per liter as my final concentration of the aluminum ions. Now, in this case, does 0.21 make sense? Well, I have 500 milliliters of 0.2, and I have 100 milliliters of 0.3. So I really can't get below 0.2, but I got a whole bunch of it. I legally cannot get below 0.2 because I don't have anything less than 0.2. But either way, well, I guess you could get below 0.2 if you had large enough volumes of dilution, but in this case, 0.2 and 0.3 being both above concentration of 0.2, then that's the bottom ceiling, or the bottom floor. But again, my ending concentration is more like the 0.2 because I have more volume of that concentration. Lots of good stuff here. The only thing that's not really covered in this solution is going from grams to moles when you make a solution. So if we had, let's say, for example, let's go with sodium chloride, and I have 50 grams of this stuff dissolved in, let's say, 1 liter, let's say 0.15 liters of water. So I have a beaker, and I want to put some 0.15 liters of volume. Okay, and I want to get this thing in, how many moles are inside this thing? What's the concentration? I got to convert this thing here into moles, and that's something you should be able to do. We have 50 grams, get rid of the grams, go to the moles, 1 mole. How much does 1 mole of this thing weigh? That's a proportion here, and it's 20 33 approximately and 34.5 approximately. So we're talking 50, let's go 58. We'll round it just for the sake of this video. So I have less than 1 mole. 1 mole weighs 50, I have less. 0.8-ish, let's do the actual math. 50 divided by 58 is 0.86 moles. So 0.86 moles of actual solid divided by 0.15 liters. This number is bigger than 1 divided by 0.15 liters, and I get considerably 5.7 moles per liter. Okay. Other than that, some common questions that will be asked about this. If I have, let's say, the NaCl solution, which is going to be 5.7 moles per liter, I might ask, what is the concentration of the sodium ion, which, of course, in this case, because it's a 1-to-1 ratio, is 5.7. The chloride ion concentration is going to be also 5.7. And again, just the ions, there are 2 ions present here. So I have 0.86 moles of individual pieces, but if you look at all the pieces, it's times 2. All right? So 0.86 times 2 divided by that 0.15 liters would be giving me twice as much concentration at 11.4 moles per liter. So this is the concentration of all the ions in solution, because I am keeping track of all of my ions in solution. And of course, if they ask me for just what's the concentration of the sodium chloride, well, in this case, how many sodium chlorides do I have? Well, I have 0.86 of them, right? And it's in 0.15 liters. So this is also 5.7 moles per liter. And that's pretty much about it.